Beneath Alaska's frozen North Slope lies a substance that looks like ordinary ice, but bring it to the surface and place a flame near it, and it burns. Trapped inside its crystal structure is natural gas, not inside one underground cavern, not inside a conventional gas reservoir, but locked within microscopic cages of water, buried beneath the Arctic permafrost. Scientists have spent decades trying to release that gas. They have drilled experimental wells, injected carbon dioxide underground, reduced reservoir pressure, and recently completed one of the longest gas hydrate production tests ever attempted. The results could help determine whether this strange frozen substance remains a scientific curiosity or becomes an entirely new category of energy resource. But the largest obstacle is no longer proving that the gas can flow. It is proving that it can keep flowing long enough, safely enough, and cheaply enough to build an industry around it. Because the moment engineers release the methane, the frozen reservoir holding it begins to change. Alaska's North Slope is already one of America's most important petroleum regions. For decades, companies have drilled through the frozen ground around Prudhoe Bay in search of conventional oil and natural gas. But during those operations, well logs began revealing something unusual in the shallower rocks above some of the major oil fields. Certain layers responded as though their pore spaces were filled with ice, yet these layers were too deep and too insulated to contain ordinary frozen water. Researchers eventually confirmed that portions of the sand contained gas hydrate, an ice-like combination of water and methane, stable only under specific conditions of low temperature and high pressure. The deposits exist beneath and around the thick Arctic permafrost, but they do not form one continuous frozen gas field stretching beneath all of Alaska. They occupy separate bodies of porous rock, bounded by geological structures, faults, seals, and underground water contacts. Some lie above conventional petroleum reservoirs that generated enormous quantities of methane over millions of years. That methane migrated upward. Then, the cold trapped it. But the same conditions that preserved the resource also created the cage that now prevents it from escaping. Methane hydrate is sometimes described as frozen natural gas, but the methane itself is not simply a solid block of gas. Water molecules arrange themselves into rigid cage-like structures. Inside each cage sits a molecule of methane. The result resembles ice, but behaves very differently. When the hydrate is brought outside the pressure and temperature conditions that keep it stable, the crystal structure breaks apart. It separates into liquid water and methane gas, and the amount of gas stored inside that solid can be enormous. 1 cubic foot of methane hydrate can release approximately 164 cubic feet of natural gas at the surface. That storage efficiency is what makes hydrates so intriguing. A relatively small volume of solid material can contain a much larger volume of usable gas, but it also creates the central problem. Producing the methane means deliberately destroying the structure that stores it. A conventional gas field becomes emptier as gas is removed. A gas hydrate reservoir changes from a solid into gas and water while it is being produced, and that transformation affects almost everything happening underground. The North Slope contains an unusually favorable combination of ingredients. The first is methane. Some of it was created by microorganisms breaking down organic material in shallow sediments. Much more migrated upward from deeper petroleum systems, where heat transformed buried organic matter into oil and natural gas. The second ingredient is porous rock. The most promising hydrate deposits are not scattered randomly through frozen mud. They occur in sand-rich reservoirs, where connected pore spaces can store concentrated amounts of hydrate and potentially allow released gas and water to move toward a well. In some tested North Slope sands, researchers have estimated that gas hydrate occupies a large majority of the available pore space. The third ingredient is the Arctic environment. Low surface temperatures create thick permafrost. Below it, underground pressure increases with depth. Where the pressure is high enough and the temperature remains low enough, methane and water can remain locked together as hydrate. But this stability zone has limits. Move outside the correct pressure and temperature range, and the hydrate begins to dissociate. For engineers, that weakness became the possible solution. They did not need to dig out the frozen material. They needed to change the underground conditions, holding it together. Scientists have been testing Alaska's hydrates for decades. Early wells proved that concentrated gas hydrate existed inside reservoir-quality sands beneath the North Slope, but confirming the resource was easier than producing it. In 2011, researchers installed an experimental well near Prudhoe Bay with an unusual name, Ignik Sikumi, fire in the ice. The project tested a method that attempted to replace methane molecules inside the hydrate structure with carbon dioxide. In theory, the carbon dioxide would remain trapped underground while methane was released for production. The researchers also tested depressurization by reducing pressure inside the well and allowing hydrate to separate into methane and water. The trial demonstrated that gas could be produced from the formation, but it lasted only long enough to reveal the next problem. Short experiments can show that a method works. They cannot show how quickly production will decline. They cannot reveal how much water a commercial well must handle, and they cannot prove that the reservoir will remain stable and productive over the years needed to recover its drilling cost. To answer those questions, scientists needed a test that would continue through an entire Arctic season. In 2018, an international team drilled a new scientific well inside the Greater Prudhoe Bay area. The well confirmed 2 hydrate-bearing sand reservoirs suitable for future production testing. Monitoring equipment was installed to measure underground temperature and acoustic changes. Additional wells followed. 2 became production wells. 2 others monitored how the reservoir responded as methane was released. Sensors continuously measured pressure, temperature, and strain beneath the surface. The goal was not simply to produce as much gas as possible. It was to observe how the hydrate-bearing rock changed during sustained production. Testing began in September 2023. It continued through the darkness and extreme cold of the Arctic winter. And on July 30th, 2024, the Department of Energy and its partners completed the extended experiment. The test generated months of information about long-term production behavior and possible environmental effects. It was an important scientific milestone, but completing the experiment did not mean Alaska had created a commercial gas hydrate field. It meant researchers finally had enough data to begin asking whether one might be possible. Every gas reservoir changes during production. Pressure falls, fluids move, gas becomes harder to recover. But a hydrate reservoir adds another layer of complexity. The material storing the methane is itself disappearing. As pressure is reduced, the hydrate separates into gas and water. That can change the temperature of the reservoir. It can change how easily fluids move through the sand, and it can change how the sediment responds to stress. A well may produce strongly at first, then slow as the surrounding formation cools or water begins restricting the flow of gas. The pressure reduction must also spread far enough into the reservoir to dissociate hydrate beyond the immediate area around the well. Too little pressure change, and much of the methane remains trapped. Too aggressive a change, and engineers may create water handling, sand production, or well stability problems. This is why the recent test mattered. Scientists already knew that depressurization could release methane. They needed to understand whether the process could be sustained and controlled, and the possible reward beneath Alaska was far larger than the experimental site alone suggested. Using seismic imaging, well information, reservoir modeling, and an improved understanding of gas hydrate geology, the United States Geological Survey assessed how much methane might be recoverable beneath Alaska's North Slope. Its mean estimate was 53.8 trillion cubic feet of undiscovered, technically recoverable natural gas. That estimate applies specifically to gas stored within North Slope hydrate formations. It does not describe all methane physically present underground, and it is not the amount inside one proven field. It represents gas that scientists estimate could potentially be discovered and produced using existing types of drilling technology. The assessment range is uncertain because most of the resource has never been directly tested by production wells. But even the central estimate is enormous, and yet the most important part of the assessment is not the number. It is what the number does not mean. Technically recoverable does not mean commercially recoverable. It does not mean 53.8 trillion cubic feet are ready to enter a pipeline. It does not mean companies have proven reserves, and it does not mean anyone currently knows how much a full-scale hydrate well would cost. The United States Geological Survey assessment assumes the gas can be produced using existing forms of well technology, supported by field experiments and reservoir models. But there is still no established commercial industry producing natural gas from hydrate formations. The economics remain uncertain. A company would need to drill and operate wells in the Arctic, handle potentially large quantities of water, monitor the changing reservoir, maintain gas production as pressure and temperature evolve, and then move the gas to a market capable of paying enough to justify the entire operation. Alaska already contains large quantities of conventional natural gas that remain difficult to monetize because the North Slope is far from major population centers and lacks a simple connection to the wider American gas market. Gas Hydrate must compete not only with those conventional resources, but also with abundant shale gas from the rest of the United States. The science has moved forward. The business case has not caught up. The importance of Alaska extends beyond the amount of gas beneath the North Slope. Gas hydrates also occur beneath deep ocean floors around the world. Many of those offshore deposits are more difficult and expensive to study than the accumulations beneath Arctic permafrost. Alaska offers something rare. Researchers can test hydrate production near an established oil field with roads, drilling equipment, geological data, and surface infrastructure already nearby. That makes the North Slope a natural laboratory. The techniques developed there could help scientists evaluate hydrate resources in places such as the Gulf of Mexico and offshore Japan. The wells can test how depressurization spreads, how quickly methane is released, how much water reaches the surface, how the sediment changes, and whether sustained production rates can ever approach commercial levels. Alaska may therefore determine whether gas hydrate remains permanently outside the global energy industry, not because Alaska's frozen gas must be produced first, but because it may be the best place to learn whether any large hydrate resource can be produced at all. The frozen gas field beneath Alaska could change everything, but not because scientists discovered one enormous block of fuel waiting beneath the ice. The methane is trapped throughout porous sand, inside microscopic cages formed from water molecules. Engineers have learned how to break those cages by reducing underground pressure. They have released methane from experimental wells, and they have now completed a long-duration test designed to reveal how the reservoir behaves as it produces. The estimated resource may contain nearly 54 trillion cubic feet of technically recoverable gas. But a successful experiment is not the same as a commercial industry. The hydrate breaks apart. Water enters the reservoir, temperature and pressure change, and every cubic foot of methane must still be produced cheaply enough to compete with easier gas elsewhere. Alaska may already contain the resource. Scientists may already understand how to make some of it flow. What they have not yet proven is whether they can keep it flowing profitably, because the gas is no longer the greatest mystery. What remains frozen is the business case.